good day to everyone, and I'm very pleased to have Professor Jean Heffernan with us today to share her perspective and most recent work on the COVID-19 immunity. Jane, as many of you know, is leading and the most dynamic and productive mathematical modelers working specifically actively in the immunology side, and she is a member of the National Task Force Immunology, and she is the leader of this NSERC EDIM Network Mathematical Public Health project on immunology, and most recently Jane was inducted to the new college of the new college of scholars of the Royal Society of Canada for her substantial achievements in many different areas, but in particular in the modeling immunology. Jane is also was the director of the Center for Disease Modeling, and she's directing as well the her immunology lab at York. So I'm very pleased to have Jane, my colleague, here. Jane, it's your time.
Thanks, Jen Hong. Thank you so much for the introduction, and thank you for having me give this seminar, though I think that we also volunteered myself too for this. Okay. So can everyone see my screen?
Yes.
Okay. So I'm going to speak about modeling immunity, and I'm going to incorporate some aspects of immunology modeling in here, and then talk about how this can be integrated into population level models of disease dynamics, and then look at distributions of immunity specifically for COVID-19 in the Canadian population. So I'm interested in modeling immunity. And so what that means is I focus a lot of my work on modeling in-host infection and vaccination dynamics. And then what we do is we try to translate the information that we find here, or that we gain from reading immunology studies too, there's a lot of that in my work, into trying to understand degrees of susceptibility that are informed by an individual's immune system and their immunity, and then trying to quantify the transmissibility of an individual to other people or to the environment in a population, and that is also going to be determined by someone's immune system. And so specifically, we look at two aspects of immunity. We look at the development of immunity in antibodies and B cell memory cells. And then we also look at the development of immunity in CD4 and CD8 T cells. And when you look at different aspects of immunity, what you're doing is you're looking at two levels of protection. One level of protection is protection against infection. We call that neutralizing immunity. And then the other level is protection against severity of disease. And so that means that you have a milder infection. So we look at those two aspects. And so we have susceptibility that really has to do with whether the degree that an individual has neutralizing immunity. And then if they do become infected, if their neutralizing immunity is not sufficient, then we look at the second level of immunity that protects them from severe outcomes from the infection as well. And then definitely when you look at a difference in severity of infection, severity in disease, then that means that you also have a difference in a pathogen load inside the host. And then that's going to change their transmissibility at the population level. So everything is going to be affecting that reproduction number at the population level. So we need to integrate an individual level of measurement of immunity into a population level to really get to understand what actual protection at the population level looks like. So we look at how pathogen and the immune response interact. We look at if an individual has no immunity at the time of infection, we look at the outcome of their infection, and then we can, in our in-host models, we can give the individual an exposure to a pathogen some days later or weeks later, and we look to see what happens. So look at how effective their neutralizing immunity is, and then we can look at exposing our individual a few years later to look at again whether they have that neutralizing immunity, or if they do, what probability it is that they can still be infected. And then in all these cases, we also look at how their immune system can be boosted so they can gain more immunity from exposures to the pathogen. And we also look at how sick or transmissible someone will be. We try to get mathematical definitions of that using these in-host models. So we look at how someone's going to feel. This is going to be proportional to the activity of their immune response, as well as the symptomatic, like the rashes that you can see for some infectious diseases. That's an outcome of an active immune response. We try to determine what level of symptoms someone will have. And then we try to correlate that also to the viral load in the body. And then we try to quantify whether individuals are going to have asymptomatic transmission versus symptomatic transmission. So we do the same thing. We look at in-host models for vaccination. So we provide vaccine doses to our simulations of the immune response. And then we look at how immunity is gained from different types of vaccines. And specifically during COVID, we've been looking at adenovirus vaccines like AstraZeneca, mRNA vaccines like Pfizer and Mrna, and protein subunit vaccines like COVAX. So we also perturb the immune response here. We look at how immunity is generated in the neutralizing component and the protection against severe infection. And then when we look at immunity over time, we also always try to quantify the waning rate that immunity may have in these individuals from vaccination or infection. And effectively, so we're trying to look at the effective immunity that an individual has, and whether that means that their immune memory cells are decaying over time, or their antibodies are decaying over time, or it could mean something like when you consider influenza, where the virus gains mutations over time, and then the immunity that someone has gained from a previous infection or vaccination decays in its efficacy against the new strains. So we look at effective immunity. When we're considering how transmissible someone is into the population, we also need to take into consideration their behavior. And when we look at, so we also have models of individual behavior, and the models are actually quite similar to looking at the immune response. So you have individuals who, you think about immunity, they get infected or they get vaccinated, and then their viral load increases and their immune system, their immune memory increases and then can decay over time. In terms of behavior, you can think about how in response to a virus or a pathogen in the population, an individual will change their behavior. So they'll increase their behavior, their protective behavior, which is going to decrease their probability of being infected. And then their behavior can naturally just wane back to their everyday practices that they're used to over time as well. So we look at that. Of course, we look at the risk of infections being imported from different places around the world, but we're more interested in my lab, which is called the Modeling Infection and Immunity Lab at York and in the Center for Disease Modeling. We're more interested in looking at how immune systems are moving around the world. And so, of course, we're going to look at different distributions of immunity in a population. And then that means we need to take into consideration all of the different types of immune systems that a population can have. So that means we also look at emigration and immigration into different geographic regions. And so if you think about a city like Toronto, where Toronto has a very large immigrant population, then we need to take into consideration what vaccine schedules look like in other countries where our immigrants are coming from. And we also need to look at the prevalence of different infectious diseases in those countries, so that when immigrants come into the population of Toronto with specific age, in specific age brackets, then we can try to quantify what their immunity is going to look like. And then we can put that into our calculations of the distribution of immunity, so that we get an idea of what total protective levels we have against specific pathogens in the population are. And then, of course, you can think that in Toronto, the distribution of immunity will be very different compared to, say, Regina in Saskatchewan, where the population ratios of immigrants to non-immigrants are very different. Okay. So just to reiterate, we look at how immunity is developed after infection or vaccination. When we have an infection or a vaccination, you can think about how you're bumping someone up some conveyor belt, and then they'll start moving down that conveyor belt unless they become exposed again, or maybe they're vaccinated and then they can be bumped back up that conveyor belt. So their immunity can decay over time, or you can think that the rate at which this conveyor belt turns also has to do with the rate at which evolution or new viral strains are developed for specific pathogens like influenza and like SARS-CoV-2. Okay, so just I want to touch back on what the most popular kind of structure of a disease model is, and then talk about how immunity is actually incorporated into these things. So this is the basic model of mathematical epidemiology. So we've separated the population into 3 different cohorts. We have our susceptible individuals that are totally susceptible. We have individuals that are infected, that transmit the virus with this rate beta. And then we have individuals that are recovered or removed. And we'll say here that these individuals have perfect immunity and will no longer be susceptible. And so here's our neat little infectious disease model, the SIR. You can see we're depleting our susceptible population over time, and they convert into infecteds, and then the infecteds convert into our recovered population. And so here in this basic model, we have 2 levels of immunity. We have total susceptibility and neutralizing immunity. Okay, so, but we just discussed how these different parameters and these different levels of immunity are going to change. So we should have more levels of susceptibility. We should have more levels of immunity. And in fact, we should have an arrow that goes back to susceptibility. And then depending on what our population looks like, or our individuals, our average individual in the population, our infectivity, our beta is going to change, as well as when an individual has some immunity at the time of exposure and they become infected, their time that they spend in the infectious class can change too. Okay. So here's an SEIR model, which is more applicable to COVID-19. Here we've incorporated natural birth and natural death into the population as well. And this is just to build on the previous slide to say that when you also are considering this exposed class where someone's infected and but not infectious, this time that an individual spends in the exposed class can also depend on the level of immunity that they had at the time of exposure. And so this total time that an individual spends in E and I can shorten as an individual's immunity increases. Okay, and then of course that this is also going to affect the reproduction number. So we look at the basic reproductive ratio, or reproduction number, which is the total number of secondary infections produced by an initial infective in a totally susceptible population. But our population, when we incorporate immunity into the population, or these distributions of susceptibility, this is also going to change what our reproduction number, how our reproduction number should be calculated. And so instead, we'll call it an effective reproduction number, or even a control reproduction number. And so, but when we try to measure our basic reproduction number, then we can only measure, we have to remove all the individuals that have immunity out of our calculation, and then we can only consider the people who are totally susceptible when we look at this, at the basic reproduction number. If we're looking at effective reproduction number, then we have to have some averages over the susceptibility over the entire population. Okay, but I'm going to relate the basic reproduction number to this idea of herd immunity. So herd immunity is defined as the entire population being protected from infection. So it's the fraction of the population that has immunity that essentially makes the whole population protected. And if you look at the CIHR model from the previous couple slides, or the SIR model, you can derive what this herd immunity threshold looks like. And it's related to this critical immunity threshold, which here I'm calling critical vaccination threshold. And if you derive it from these simple models, what you're going to get is that the fraction of the population that needs to have immunity in order for you to have a population that's totally protected against infection, this is equal to 1 minus 1 over the basic reproduction number. Okay. And so if we look at different pathogens of interest, and we look at their basic reproduction numbers, then we see that for measles, we need 91 to 95% of the population to have immunity. Our vaccine that we have for measles is 95% effective. So that means that if, say, 100 people go get vaccinated, then 95 people will actually get immunity from the vaccine. And then that's why we have a booster dose, to try to kind of catch up to get those individuals that didn't get immunity from the previous dose, but also to boost all the other people that did get immunity from the first dose as well. So this means that everyone needs to go get immunity in order for the population to be protected from measles. For pertussis, we see something kind of similar. We go down to, this is 2003 SARS, so we have 50 to 80%. For seasonal influenza, depending on the reproduction number, if a reproduction number is equal to 1, then the critical vaccination threshold is quite low. But if it goes up to 3, then it's about 67%. But it's important to realize that all of these critical vaccination thresholds are derived using an SIR model or SEIR model, where you have individuals that go into this recovered class either from infection, or they can move directly to that recovered class with vaccination. And then it assumes that those individuals are there for the rest of their life. Okay, so they have lifelong immunity. But we know in practice that for a lot of pathogens, this isn't true. And so this means that for every year or periodically, we need to, every year for influenza or periodically for other infectious diseases, we need to do something called a catch-up campaign, where we give say individuals from certain age cohorts need to then go and get some booster dose against a pathogen in order for them to maintain their immunity above a certain threshold, so that they have neutralizing immunity, so that we can gain that herd immunity component in our population. But this is also effectively affected by the vaccine efficacy as well. So if our vaccine is not effective in providing neutralizing immunity up to a certain point, then these numbers can even also increase considerably to even over 100%. So that's something that we need to discuss as well for COVID-19. So suppose we have a reproduction number of around 5, which was true for something close to the alpha strain, then it means, so if we have a vaccine of 80% effective in generating neutralizing immunity, then we would need 100% of the population to get the vaccine in order for us to have herd immunity. If the vaccine's 95% effective in generating neutralizing immunity against the alpha strain, then we need 85% of the population to get the vaccine in order for the whole population to be protected. But we also then, when we consider these calculations for vaccine efficacy and this critical vaccination threshold for herd immunity, we need to also consider a vaccine hesitancy. And vaccine hesitancy during COVID has ranged from 10 to 25%, depending on the population and the age cohort. And adults in Canada roughly make up about 80% of the population. So what these calculations say is that if we have a vaccine that has a lower efficacy, where 80% still pretty good, or a high level of efficacy, 95%, that means that we still need all adults to go get vaccinated. And when we expand, because we know that children are now able to get vaccinated, children 5 and up, and all those appointments have been released starting today. It means that we even need to, when we're considering the fact that COVID-19 immunity can wane over time, we need all of the children to also go get vaccinated in order for the population to gain what's called herd immunity. And then we should consider that this herd immunity component is temporary because immunity can decay over time, especially if the pathogen is not around to expose people again to boost their immunity. So we need to consider then booster vaccination campaigns for COVID-19 vaccines, especially in individuals that have higher rates of waning immunity, like those who have comorbidities and those who are in older age groups. Okay, so this is just very similar to what I was just saying. So when you look at infectious disease models, you can also extend the SEIR model to incorporate many other things like metapopulations, networks, age. In COVID-19, age has been important, and I'll touch on that a little bit later, spatial models, immigration, and so on. And then in the infectious disease model, you can add many other compartments for the individuals to go into. So we have vaccinated compartments, compartments for partially immune people, people who have asymptomatic infections and are infectious, people who may become chronically infected, and so on. And so you can look at an infectious disease model that kind of looks like this, where SEIR, you can add another asymptomatic infection compartment here in between E and I, for example, and maybe that also goes to R. Here's our chronically infected people, who are people who move into the vaccinated class and their immunity can wane, but maybe can be boosted back up again through vaccination. We have people who have recovered and their immunity is temporary, and so on. But in all of this, you can see this little star. Well, this star means that there are lots of other characteristics of individuals in the population that can help define this graph. And so you can think that this model might look a little bit, all these rates on all of these arrows might be different for someone who is 10 years old versus someone who's 50 versus someone who's 80. Also, they'll be different for someone who has a high level of immunity versus a low level of immunity versus some medium level of immunity. These can also be affected by genetics and like ethnicity. They can also be affected by an individual's work. Certainly, there are differences between levels of exposure to infectious diseases for teachers and healthcare workers compared to someone who works from home, for example. There are lots of different things that we can incorporate into this star, as well as just where the person lives. Do they live in an urban area versus a rural area? Do they live in what country do they live in? And so on. How big is their family? How many people do they live with? How often do they see other members of the community? There are all these different things that we need to consider in this graph as well. Okay, but I'm going to focus just on the structure for immunity in individuals. And so we'll just briefly look at some immunology work that we've been doing, and then we'll extend this to look at a model of immunity over a population. Okay, so when you look at immunology, then you also have to take into consideration how a pathogen interacts with cells in the body. And so when we look, this is the basic model of pathogen dynamics in the body, where you have susceptible cells. Susceptible cells are born and they have a death rate, and they can become an infected cell when they meet a virus or a pathogen. So then we have here are our infected cells. Our infected cells also have a death rate, and our infected cells become factories to produce new virus particles. And then our virus particles have a clearance rate from the body, and they can also be lost into the healthy cells during the infection process. In an in-host model, we also have a reproduction number. We can consider, so here's an infectious pathogen or infectious virus particle. The virus particle infects a cell, so we make a new infected cell. And then the infected cell produces virus particles. The infected cell can produce two types of virus particles, infectious or non-infectious. The blue ones here are infectious and the yellow ones are non-infectious. And so this means that the reproduction number here is 4. So we have 4 new infectious virus particles made by 1 infectious virus particle. The reason why we'll still keep track of the non-infectious virus is that if an individual has their viral load measured, you're ultimately measuring their total viral load. So it's the combination of the non-infectious and the infectious virus. You need to take that into consideration when you're looking at in-host models, especially if you're trying to fit your in-host models to data. Okay, so if we look at different types of treatment that can be provided to individuals who are infected, then there are some things that we want to do to decrease the reproduction number. So here's the reproduction number for this simple model of in-host infection. So something that we'd want to do is we want to decrease the rate at which cells can be infected. So that's this beta up here. And we want to decrease the number of virus particles, infectious virus particles that the cell can make. So that's decreasing this K. You could also decrease the lifetime of the infected cell, and that's going to be affected by the immune response too, but drug therapies can do that. And then you can also have drug therapies that can affect this decay rate of the virus. If you're looking at the immune system stimulation, then you can certainly help block the infection of healthy target cells through something like interferon. It can block infection. You can have an increase in the killing rate of infected cells. That's through CD8 T cells or cytotoxic T lymphocytes. They go and kill infected cells. You can increase the clearance rate of the virus in the body. That's related to antibodies. And then you can also decrease you can increase the rate at which the virus particles are lost in the immune response as well. But you have to be careful here that if you want to decrease the infection of healthy target cells, then you're also decreasing this, but you want to increase this because you want to increase things in the denominator. And so there are some things that you can do, like inputting decoy cells that help activate the immune response and at the same time absorb virus into them so that the virus can't replicate. Okay, so here's a simple extension of the basic model of in-host dynamics where we incorporate this thing called interferon. Interferon is secreted by some components of the immune response that we can assume are proportional to the infected cells. So we have interferon here, and then interferon can be absorbed into the healthy target cells, and then they become refractory cells, which are resistant to infection. You can also extend the model to look at B cells and antibodies. So activated B cells become plasma cells, which then can produce antibodies. You can look at 2 different strains in the body or 2 different pathogens in the body and look at competition. You can also incorporate CD4 and CD8 T cells. So we have naive cells, they become activated. And when they're activated, depending on whether they're CD4 or CD8 cells, they have different activities that they have in the body. And then we look at the generation of the memory T cells. There are also components of the immune system that are in the innate immune response that can be that can increase in proportion and decrease in proportion depending on what you're modeling. Here's a model that we use to look at adenovirus vaccine for COVID-19, where we've been trying to capture the dynamics or the effects for all of these different cells in the immune response. But we only have a limited amount of data, so we have to simplify the model to just these components to see if we can accurately produce outcomes of adenovirus vaccine in individuals. Then here's just also a very simple model where we look at the naive cells that become activated and then memory, and then we can expose these individuals with these different in-host models of vaccination or infection that can be memory. We can expose these individuals at some time later to a pathogen and look at their neutralizing immunity, and then if they get infected, we look at the change in their infection curve to look at severity of disease and their transmissibility. And that just has to do with that. So here's an idea where we can look at the area underneath the curve. And then, so here's an individual that has some high level of immunity at the time of infection, and they have an asymptomatic infection if we look at the area under the curve, versus someone here who has a high level of infected cells. They're going to have a lot of transmissibility. And then we also look at the peak here that has to do with the occurrence of symptoms. And so this would be a symptomatic infection, whereas this individual has an asymptomatic infection. And like I said before, at the time of infection, we know what an individual's immune system status is. And then after infection, we can see what they're boosted to. So here's an individual that had about 150, level 150 of immunity at the time of infection. And after infection was cleared, they have level 210, it looks like. Okay. So now I'm going to just quickly note that when you're looking at models of the immune system and models of immunity at the population level, there's lots of different things that you can consider. Like I said, in these stars, I've got all the age and the immune system and where individuals live. But just having a couple of components, like just neutralizing immunity and immunity against severe infection, can give you so many equations. So you can be working with 5,000 equations and just be considering 2 aspects of immunity, which is crazy. So a lot of work has to go into looking at how to simplify models so that we can gain information that we need, only the information that we need to replicate what's actually happening in the population. The same thing happens with in-host models. There's so many different components of the immune response. And not actually a lot of data that we can use from measurements of the immune response and of infections. So you might want to develop this huge model of the immune system, but you're going to incorporate so much uncertainty into that. So you need to really simplify the model down in dimensions so that you can get new knowledge from your model. So essentially what you want to look at is if you have biology incorporated into the model, you want to only incorporate enough biology so that you can get some new knowledge from results. So that's an optimization problem that we're looking at all the time. Okay, so now I'll just quickly look at a couple of projects that we've been doing for COVID-19. So here is a model that we've looked at for AstraZeneca, or adenovirus vaccine like AstraZeneca. So what we did is we looked at what our immune system levels will look like after 1 dose of vaccine and 2 doses. And we fit this mathematical model to the data. So here you can see, here's our model, which is the blue line for one dose of vaccine. And here's our model, the blue line, and then the red line is 2 doses of vaccine. And here we're looking at concentration of IgG. And we fit this to the data. So we have individuals that are of certain age groups and whether they have 1 dose or 2 doses of vaccine. At the same time that we fit to the IgG data, we also fit to interferon gamma. So here's our 1 dose individual, and then here's 1 dose and then 2 doses. So what we do is we fit the model to data taken from individuals in this clinical trial. And we were interested in looking at what happens if you give an individual the first dose at the appropriate dosage level, and then you give an individual their second dose sometime later. So we look at different time spans between the first and second dose. But we also look at what happens when you take different time spans between the first and second dose, and then you give the second dose at half the size or even a quarter of the size. And so what our ultimate interest was here was trying to look at a conservation of vaccine, so that if you provide the first dose and then the second dose is some fraction of that dosage level, then you can have more vaccine spread out to more people. But we also need to make sure that our immune system, the immunity generated from that type of combination, is something that will be effective. And ultimately what we found when we looked at all of these different considerations of time between doses and dose size, that for a lot of these cases, we were still able to generate a level of immunity in the individual that's of similar measure to the immunity that someone gains after COVID-19 infection. And so these scenarios of different times between doses and different dose sizes for the second dose are something that can be considered in when doses are limited. Okay, and so there's just some more results looking at different aspects of the immune response. We also looked at mRNA vaccines. So here's a figure where we fit a similar model to the AstraZeneca project, but here we have lipid nanoparticles. The model is just slightly different. And then we fit our mathematical model to different data sets, and I'm just showing you the IgG response here for Pfizer and Moderna clinical trials. And so here our Pfizer clinical trial data is in red. This is all gathered from papers in the literature. The Moderna clinical trial data is in green, but these are done by different labs, and these are in arbitrary units, so you can't actually do a comparison between the Pfizer and Moderna data, except if you have a lab that has done both. And so you can see here that there's one study that has Pfizer and Moderna clinical trial data that we looked at. So we took 22 studies of Pfizer and Moderna, and we fit our mathematical model to try to quantify the decay in immunity that someone can have over time. And so if we look at 2 standard doses of either vaccine, we can see that by day 212, 99% of the antibodies that they've gained from vaccination will have left. Okay, if we just look at Pfizer, we see that 99%, we have 99% loss by day 190. And if we look at just a Moderna clinical trial data, this happens by day 232. And so we were interested in looking at this study because at one point it was recommended that a third, like a booster dose of the mRNA vaccines be provided to individuals by 265 days post dose 1. And what we found here is that this actually should be shortened, and it should be shortened to about 6 months. And while we were doing this study, that's the Center for Disease Control in the US came out, and at first they were recommending around 8 months after the first dose, and then they shortened that to 6 months when we were doing the study. So our modeling results confirmed it. We also were able to look at how antibody outcome might differ between male and female. So you can see that there's not that much difference, so we weren't able to get a lot of information from that. We also looked at the different decay rates or immune response levels in individuals of different age groups. And here we've been able to show that individuals that are in older age groups have a higher rate of decay in their immunity compared to individuals that are younger. I'll note that this is only looking at IgG here, and so this is related to neutralizing immunity. We didn't work with any data here looking at T cells, and so we're only looking at neutralizing immunity when we're looking at this, and we're not actually able to say what neutralizing level is, because this is only in arbitrary units and just a measure of IgG. But if anyone's interested, I can point you towards the manuscript that we've posted on medRxiv, where we've tried to correlate different levels of IgG response to protective capacity in terms of neutralizing immunity as well. Okay, so what we've done through all of these studies is we've really tried to inform our knowledge of the immune response from vaccination. At the same time, we've been always reading the literature on infection. And what we've tried to do is develop a mathematical model of COVID-19 infection in the population that will give us important levels of immunity that we need to consider to get a fuller picture of what immunity looks like and the effects of immunity in the population during the pandemic. And so what we did with colleagues that you'll see in these different articles here is we adopted a model that we first developed for pertussis to COVID-19. And so what we have here is we have 4 different levels of immunity. So here, individuals in S1 are totally susceptible, and individuals in S4 have neutralizing immunity. The individuals in S3 have a lower level of neutralizing immunity than in S4, and they have some immunity. They have a high level of immunity that protects them from severe disease. Individuals in S2 have a higher level of neutralizing immunity than individuals in S1 and lower than S3. And they also have protection against severe infection, but that protection level is lower than if they were in the S3 class. So we're looking at waning immunity, of neutralizing immunity, as well as immunity that protects against severity of infection. So what we do when an individual in any of these classes becomes exposed to the pathogen, we then determine whether the individual have a mild infection, a moderate infection, or severe infection. And that probability is determined by 2 things. Their level of protection against severe disease generated by the class that they're in S2 or S3 or S1. And then also looking at their comorbidity status. So for each age group that we have modeled here, we consider the distribution of comorbidities in that age group, and that then determines whether an individual have a mild infection, so that someone has no comorbidities, moderate, they have 1 comorbidity, and for severe infection, we assume 2 or more. And that information is gathered from a published article that I have on the next slide. So we also assume that individuals that have a mild infection, their level of immunity will push them towards this S2 level. If they have moderate infection, they'll move to S3. And if they have a severe infection, they'll move to S4. And this means that we assume that the immunity gained from an infection is proportional to the level of virus that someone had in their body. And so that means that we also assume that the mild infected individuals have a lower transmissibility than someone who's in the moderate infection. But in the severe infection, we also consider that these individuals have a lower transmissibility because they're staying home or they're so sick that they're going to hospital. and they're wearing masks and are under treatment. We also have, of course, implemented the vaccination, the primary course of vaccination into this model. So individuals after one dose will move to this first row of vaccine. And if they get the second dose, they'll move to the second row. But then you also see that in all of these classes where we consider immunity, we always have a waning rate. So this is denoted by the wavy squiggly lines here. So you can move from S4 to S3 to S2 to S1. And we define what these waning rates are in a sensitivity analysis. We also have waning from our first doses into these susceptible classes, S's. And then we have waning from our second doses into our susceptible classes as well. You'll see too that we've colored the vaccinated classes with similar shades of purple to the susceptible classes. And that means that we're assuming similar immune system characteristics between V1.1 here and S2, V2.1 and S3. And then we assume that all of these darker purple shades have neutralizing immunity. So in order for us to parameterize the model, we have to fit this model to data. And so we have case data that are reported daily for the different provinces of Canada and Canada in general and other countries that we've looked on. So we've also implemented this model in a study of France. And so we fit this model assuming that all case reports will definitely include our severe infections, some fraction of I3 infections, and for the most part, we've assumed that these individuals in the mild infections will only be reported if they're contact traced. And we assume that all of our case detections will actually lie somewhere between I4 and the sum of I4 and I3. Then what we do is we fit our model to case data. We also inform our vaccination strategies using projections under the NACI scenarios for vaccine rollout in Canada, or we also fit that to actual vaccine rollout data in the past. And we also have our distribution of comorbidities from this paper by Clark et al. So that informs our values of the probability of mild, moderate, and severe infection. We start out the model with a reproduction number of 2.6. And that comes from this paper by Knight and Mishra. And when we have a model where we have lots of age groups, we then need to incorporate contact structure into our model. And the contact structure is related to the public health mitigation strategies. So we have, depending on what public health mitigation components are implemented in the population, we change the contact matrix. And then we look at how individuals' behavior and in terms of compliance to the public health mitigation can be affected. And it's this compliance kappa that we first started calling it compliance. We fit this to the incidence data. However, as the epidemic evolved and we had the appearance of new variants of concern, this is also incorporated into kappa. How contact tracing rates change, testing rates change, the effect of weather on transmissibility. This kappa parameter that we fit to the data is affected by all these different things. And so if you see fluctuations in this parameter, it's actually reflecting some combination of any of these components here. Okay. So we roll out the vaccination program. We roll it out very similar to how NACI laid it out. And this is just looking at the Canadian population here, but we've also used this model to look at immunity outcomes and infection for all of the different provinces as well. Here is what the fit looks like. So we have our red is our incidence data. Our black line here is the incidence of our severe infections, and here's our dashed dotted line is our incidence of moderate and severe infections. And then this dotted line up here is our incidence of severe plus moderate plus mild. And you'll see that in all cases here, And this is kind of what this is what we're fitting, that our data should lie in between the solid line and the dashed dotted line with our assumption. And so here we're looking at different waning rates. So here we're looking at 1 year between compartments, 3 years between compartments, and no waning at all. And we're also looking at 3 different types of vaccines where we have different capacity or protection against infection, so that neutralizing immunity after the first and second doses, and protection against severe disease as well. Those are the 2 components that I talked about that are waning over time. We also looked at the indirect effects of vaccination. So early on, when vaccine was only available to individuals who are 18 years and older, we looked at what the effect of actually vaccinating individuals 10 years and up would be. And we see that because this age group has a high level of contact with the rest of the population, that all of the age groups will benefit from vaccinating this age group. And then what we did is we tried to quantify what the distribution of immunity looks like when we look at different vaccines, different waning rates, as well as different levels of susceptibility of all of our individuals, and looking at their different changes in their activity levels in the population as well. So here, the blue is looking at 1 dose of vaccine, green is 2 doses of vaccine, and then red here is when we have individuals that have gained immunity from infection, or they've gained immunity from vaccination and then have waned into the susceptible classes. And the different shading here is the different age groups. And so you can see that the lightest shades of blue and green don't exist in these plots because we don't have vaccination in these plots for these lowest age groups. Okay. So now we'll touch just briefly on what distribution of immunity looks like in the population. So this is what we fit the model to data up to about September, and then we tried to project what the fall wave would look like in Canada. And so here we're seeing that about 75% of the Canadian population has some immunity against COVID-19. But the individuals in the green class are the only ones that have neutralizing immunity. And that's certainly not up at that high level of critical immunity threshold that we would need in order for the population to have herd immunity. But what we also did is we looked at how this is going to help diminish hospitalizations and severe infections in the population. And I'll touch on that in the next slide. If we look at different vaccines, you can see and their protective capacity, as well as their different susceptibility levels in the population, you can see that we can move from something that's about 70% immunity to something where we have about 80% of the population having some immunity against COVID-19. So this is something where we instead of looking at Canada, we looked at Ontario. So here we have a distribution of immunity where now green is neutralizing immunity. So this is the S4 and 2 doses of vaccine. Here's S3 and 1 dose of vaccine from one of the classes. Here's S2 and 1 dose of vaccine from the S1 class. And these are individuals with no immunity at all. So they could have had infection and they could have had vaccination, but their immunity has waned. So we tried to use this to look at what might happen during the fall waves. We fit the data to September, and then we looked at here that there's a very large bands of susceptibility in individuals that are 12 to 29 years old. And so we used this model to say that more vaccination uptake's needed in these age groups. We looked here to see where there are increases in immunity, and we can see that there's large increases in blue and yellow, and we don't see a large increase in green. And that means that most of our infections in the fall wave are mild and moderate, though there are some severe infections. And if we look at only severe infections and the distribution of ages in those severe infections, we see that a large proportion of severe infections in the fall wave are going to be individuals in the yellow, orange, and blue classes. And so we use this to say that a third dose of vaccine is going to be needed to be provided to individuals that are age 50 plus with comorbidities. The last thing that I'll say is that we also see how our model can be affected by vaccination and looking at ascertainment rate. And of course, if you see that if the vaccine is pushing people down towards milder infection, that's going to affect how we ascertain those infections and their transmissibilities as well. And so our model right now, the way that we've applied it, we have that 1 in 3 infections is ascertained before vaccination was implemented. And in the post-vaccination era, we have an average of about 1 in 13 infections. So this work was done with lots of collaborators, and I'm listing them here, and it's been funded by a lot of different collaborations with government and through the modeling task force and through the NSERC EIDM. I can take questions. And if anybody is interested in looking at what the seroprevalence looks like for specific provinces, I do have slides for that if people want to have a look. Thank you.
Thank you, Jane, for the presentation. And wondering if any questions, comments. I noticed that Tom is the any other comments? You can raise your hand, or you can just directly speak, unmute yourself and speaking directly. Maybe I can ask the first question, James, about the new vaccination for the kids between 5 and 11. Would that change much of the picture?
Yeah, so right now there are a lot of questions still for children. So we've been in our modeling and in lots of other people's models, we've been assuming that children have the same level of susceptibility and same level of transmissibility if they're infected, though the vast majority of our children, when they're infected in this model, go to the mild infection. So we need to look at their different levels of susceptibility to see how that changes our seroprevalence estimates. But in terms of vaccination, we're really just starting to implement what that looks like in our model. And essentially, we'll see that these bands in red here are going to get much smaller. And effectively, you'll see that the green population will move up, so our neutralizing immunity, and so we'll have a higher protective capacity. I'm just not sure at which rate the protective capacity will decay. We need to also look at that in terms of the clinical trials and look at in-host modeling.
Thank you, Jean. Other questions? I have another naive question. So Jane, we're thinking about third dose, and of course in different priorities. And when it comes down to larger to the entire population, is it better to really have the third dose for the entire population at the same time, or is really good pacing in different ways so you generate a layer of immunity in the populations rather than a complete homogeneous one?
That's a good question. That's something that we've been thinking about in-host modeling, is because we've only so far in our in-host models looked at first and second dose, and we can look at, because now we have models that are good for adenovirus and mRNA vaccines, we can try to implement a third dose using the parameters that we fit. There are some studies of the booster dose that are being done through the COVID Immunity Task Force. It would be great to hear more about the results coming from those studies. But what I don't know is, we know that the third dose is effective in people who have who are immunocompromised or immunosuppressed. And I don't have any knowledge right now, because I've been focusing on some other things and haven't been keeping up in my reading on what the third dose looks like in individuals that don't have immunosuppression. So that's a good question, and something that we can try to consider in this type of model, rolling out that third dose.
Right, thank you very much, Jane. Other questions and comments? Just want to remind again that the lecture is recorded, so it will be you and your friends can visit the lecture anytime. I assume it's going to be online right away almost.
Yeah, and I'll just say thank you to everybody. I know I covered a lot of material. If you're interested in some estimates for the other provinces, you can feel free to reach out as well.
I have some noise from the background. I don't know if it has questions or not. If I don't see anybody raise their hand, I want to again thank Jane for your wonderful talk, and congratulate you, Jane, for so much of your achievement over the past 2 years. Thank you, Jane. Tom? So
Thank you, and thank you for your support.
Thank you.